Welcome back. So last time we talked about two very important types of forces, which are normal force and friction force. So today we're going to look at three of the other most important types of forces, tension, air resistance, and spring force, and we're going to see how to show them as a sketch using something called free body diagrams. So let's begin with one type of force called air resistance. You probably know that if you throw yourself from an airplane and you don't have a parachute, you will fall and die. But if you do have a parachute, you won't die because the parachute will stop you so that you don't reach the earth at such a quick speed. So that happens because all of the air gets inside of the parachute and creates a new force called air resistance. So until now, we've said that objects that are falling have one force, and that force is the force of gravity downwards. But for someone in a parachute to be able to decelerate slowly and reach a speed that won't kill him, there has to be another force upwards. So this force upwards is actually called air resistance, and we can write it as F air. So air resistance is a type of drag force. That means that it decelerates the speed. It's sort of like a friction but with air. So air resistance is the friction that an object feels with the molecules of air around it. And what we know about air resistance is that it's proportional to speed. So this force, F air, is proportional to speed. So when you initially drop from an airplane, the only force acting on you at the beginning is the force of gravity. It's your weight downwards. And there's no air resistance because you just jumped. So it's going to pull you down completely. But since it's proportional to speed, as you get a little faster downwards, then the weight is going to stay the same, the force of gravity, but there's going to start to be an air resistance upwards. This is when you're going faster. And you're going to go even faster because you're accelerating due to gravity. So a while later, maybe it looks something like the force of gravity and air resistance is a little bigger. And at some point, the force of gravity, which is the middle, which is the same, is going to be exactly the same in size as the force of air resistance. Why? Because it gets faster and faster, so air resistance gets bigger and bigger. But once it reaches the exact same size, maybe those arrows don't look the same, but they should, you're going to reach something called terminal velocity. So what happens here is that our two forces are equal. So the net force in this example, net force is 0. And remember we had Newton's law, net force equals mass times acceleration. If the net force is 0, the acceleration also has to be 0. So when the acceleration is 0, our natural consequence is that the object will move at constant speed. So at some point, the person in the parachute will start moving at a constant speed. And if the force of air resistance is proportional to speed and the speed is constant, the air resistance will also be constant. So once the object reaches this constant speed called terminal velocity, it'll keep that speed until it reaches the ground. That's why it's called terminal velocity. The terminal here just means the end speed, the speed at which it will reach the ground. And this is actually very fortunate that it happens. One example is parachutes. If terminal velocity wasn't reached, then the person in the parachute would keep increasing its speed, and would reach the earth at a very high speed and have high chances of getting injured. Another example would be raindrops. Raindrops fall faster and faster as they get away from the cloud and down to the earth. If there was no air resistance and they didn't reach a terminal velocity at some point, they would fall in our heads with such a speed that they would probably crash through our skulls and kill us. So terminal velocity is a very important thing for us. Now, there's no specific equation for the force of air resistance, but since it's proportional to speed, we can say that it's equal to speed times a constant, and this constant is usually written as b. But b can be any number. It just depends on if we're talking about a parachute or a raindrop or a coin falling from the Empire State Building. But don't worry about the equation, just know about this relationship of proportionality to speed. So you might ask, if there's no equation, we're not going to use an equation. How could we solve exercises about this? So I have an example. Suppose that a guy is bungee jumping and he throws himself downwards and he has an acceleration of -7 meters per second squared. And his mass, let's say his mass is 100 kilograms, just to make the math easier. So he has a mass of 1,000 kilograms, he's accelerating downwards at -7 meters per second squared. So you know when there's no air resistance, the acceleration due to gravity is always -9.8. So if it's not 9.8, it has to be because there's another force upwards that is stopping him a little bit. So that force has to be air resistance. So how can we calculate the air resistance acting on this guy? Well, we go back to our equation of Newton's second law. So we know that net force is equal to mass times acceleration. And the net force is the subtraction of the forces. So downwards we have the force of gravity, which is going to be negative. And then we're going to have upwards plus the force of air resistance. And this is going to be equal to mass, which is 100, times the acceleration, which is -7. So force of gravity, you can never forget that the force of gravity or the weight has the equation force of gravity equals -m times g, which is equal to -m times 9.8. We know that g is 9.8. So we can put that into our equation and we get negative mass is 100 times 9.8 plus F air equals 100 times -7. And now we just have to solve the equation. So this will give us -980 plus air resistance equals -700. And we can solve for air resistance by passing this to add. So we get air resistance is equal to -700 plus 980, which is the same as subtracting 980 minus 700, which gives us 280 newtons, right? So this is the force of air resistance, and we didn't have to use this equation of proportionality. Just know that if the acceleration was -7, it was because the force of 280 newtons had to be going opposite to the force of gravity. Now let's move on to the next force, which is tension. Okay, so the force of tension is a force caused by a stretched string or cable. That's just the definition. So anytime that there is something hanging from the ceiling with a string or a cable that you pull to its maximum length, there's going to be a tension, and that is a force. So for example, I'm going to draw, let's say this is a ceiling, and there's a lamp hanging from the ceiling. Here's a lamp that is giving off some light. So we know that everything has a force of gravity that is acting on them downwards. So we can draw an arrow for the force of gravity. However, the lamp is just laying there. So there has to be another force that is exactly the same size, but points upwards and cancels it out so that all the forces are balanced. So there has to be a force that is exactly upwards, it's exactly the same size, and that is the force that we call tension. We use T for tension. So if we're talking about an object falling through the air, the upward force is called air resistance. If we're talking about an object that is hanging, the force is called tension. It could also work if something were to be hanged like this, maybe like a necklace or something like that. There would be a force of gravity downwards, and there would be a tension in every single cable. Different tension, probably. But we're not going to worry about these types of situations yet. We only care about when there is one cable or one string and the force of gravity acting on it. So again, just like in air resistance, there's no equation for tension force. We just have to figure it out with Newton's second law. So we have Newton's second law. It tells us the net force is equal to the mass times the acceleration. And in this case, in anything that is hanging still, the acceleration is 0. So if the acceleration is 0, we can put that into our equation. And of course, if we're going to solve a problem, we need the mass. So let's say the lamp has a mass of 5 kilograms. 5 kilograms. So we put that into our equation, and we get that the net force is equal to 5 kilograms times 0. But 5 times 0 is just 0. So the net force is 0. But what makes up the net force? We have a force downwards and a force upwards. The downwards force is negative Fg, and the upwards force is tension, and that is equal to the net force, which is 0. So we can put that into the equation, and we know that negative gravity plus tension equals 0. So if we pass gravity to the other side, we get the following equation. Tension equals force of gravity. So always, when there is an object hanging by a single string, and it's still with no acceleration, not moving, we can say that the tension is exactly equal to the force of gravity. So this is the mathematical way. This is just the logical way. The arrows have to be the same size and they have to point exactly in opposite directions. Now let's move on to our third type of force, which is the spring force. So the spring force is defined as the force that every spring makes when it's either stretched or compressed. Spring is un resorte. So when you compress it or stretch it, you're going to feel a force, and that is the spring force. So let's draw an example of how that looks. Maybe we have a table here, and there is a spring connected to it. It has a normal length, whatever, maybe like this, and there is a big box attached to it. So this is the spring when no one is touching it and no one is doing anything to it. But now imagine that we have the same spring, but someone stretches it. So now the distance between each of the rings is bigger. So there's one here, there's one here, there's one here, and we took the box all the way over here. So before, the box was here. Let's say about here. And it was stretched all the way here. So basically, if we were to measure how stretched the spring is, we can take the middle of the box before stretching it and the middle of the box after stretching it, and this would be the distance that we can call x, as we've always called horizontal distance. So x is how much it was stretched. We could also have compressed spring, and it would look something like this. And the box is here. And before, it used to be all the way over here. So if we wanted to see how compressed the spring is, we would see where the box was before, the center of the box, and where it is now, and this would be the compression distance. So this is a compressed spring, and this is a stretched or elongated string. Both will cause a force. If you've tried to compress a spring and you let go, you will see that it pushes back to its original position. And if you stretch it and you let go, it also pushes back to its original position. That is a force. But there's something else that we need before we define the equation for a force, and that is what spring it is, what type of spring it is, and that is given by a constant K. So every spring has its own constant K. It's the same no matter how far you stretch it or compress it, and K is just called the spring constant, or the spring stiffness constant. And it tells us how hard it is to stretch and compress a spring. The bigger that number, the harder it is to compress a spring, and the harder it is to stretch it. So that just tells us how stiff the spring is. And now we're ready to give the equation for the spring force. So the spring force, which we can call Fs, is going to be equal to negative K times X. So again, K is the spring stiffness constant, X is the distance of compression or elongation, and our equation is equal to negative K times X. The negative just means that if you stretch to the right, the force you're feeling is to the left, back to the original position, And if you stretch to the left, the force you feel is to the right. So that's what the negative means. And this is actually something called Hooke's law. Hooke was the guy that discovered that this is the equation for the force made by a spring. So I could give you an exercise in which I say, how much force would a spring do if I stretch it 5 centimeters and it has a stiffness constant or spring constant of 20 newtons per centimeter. And you just have to put these values inside and see what it gives for the force. Now that we saw the 3 types of forces that I wanted to show you today, let's move on to the way to sketch forces, which is called free body diagrams. So free body diagrams are a diagram, a type of visual representation of the forces acting on an object in each situation or circumstance. So basically we can say it's a sketch of the direction and the magnitude of all of the forces acting on an object. So let's write that down. So hopefully you remember from when we saw vectors. Force is a vector, so it has a magnitude and a direction. And that's why free body diagrams are so useful, because they give us both. They give us magnitude and they give us direction. So with a free body diagram, we can basically think about all the vectors and the vector forces acting on an object. So let's see how it's done. So I give you a situation and you draw the object usually as just a circle. Whatever object it is, if it's a ball, if it's a box, if it's a person, if it's a book, you usually just draw it as a ball. And I tell you the situation and you have to list all the forces acting on it and draw each one as an arrow. And the arrow has to be with a length that represents the magnitude, how big it is, and pointing in the direction of the actual force. So let's say, a first example, a person falling down from an airplane. So we saw this one before, and we actually did do a free body diagram without you knowing that was what it was called. So there are actually 2 forces acting on a person falling from an airplane. There is the force of gravity, or weight, which we're going to draw as an arrow of any size, downwards, and label it as force of gravity. So all forces need to have an arrow with a size and a direction, and they need to have a label. In this case, Fg. Now, what other force acts on the person falling from the airplane? Air resistance, we just saw it. So we need an arrow upwards called F air. But we need to remember that it can never be bigger than the weight, because if not, the person would go upwards when they throw themselves from the airplane. So it can either be exactly the same or a little smaller. I'm going to draw it a little smaller just so that I don't get confused. F air. And that's it. That's a complete free body diagram for a person falling from an airplane. Let's do another example. Let's do a book sitting on a table. So we have a book. We can also draw it as a circle. If you want, we can draw the table just so that we know what we're talking about. And let's label it book lying on a table. So some of you might say, okay, if it's not moving, there are no forces acting on it. But remember that everything always has a weight. There's always a force of gravity. So as soon as they tell you draw a free body diagram, the first thing you should do, just by instinct, is to make an arrow downwards and call it force of gravity. That's the first thing you do. Then you think, okay, if it's not moving, there's no acceleration, there has to be an upward force that is exactly the same size. Hopefully that looks the same size. What is it? And we learned last class that that force is called normal force. So we put Fn for normal force. Since it's not moving, it's not going anywhere, that's it. We're done with the diagram of a book lying on a table. Let's do a third diagram. Let's do a person holding on to a rope. So we have a person. We can also draw him as just a dot. And let's say person hanging from a rope. So again, as an instinct, the first thing you have to do is draw the force of gravity downwards. Always, always, always. There's no case in which there's no force of gravity unless we're in space, and we're not going to be talking about space. So the person is just hanging there. He's not falling, he's not accelerating. So there has to be an upward force of exactly the same size upwards. What is that force? It's one of the ones we saw today. Since there is a rope, any rope, string, cable gives us a tension force. So the upward force is tension. And there is no movement or acceleration to the sides, so we're done. That's it for our diagram for a person hanging from a rope. And now let's do one that's a little bit more complicated. Let's do a box being pushed through a rough surface and there is friction. So we can again draw it as a circle, but if you want to remember, we could put this to remember that there's friction. Of course you don't need it, but that's it, that's just a reminder. So this is box being pushed through a rough surface. So again, before we start thinking about the pushing, the first thing we do is draw the force of gravity downwards. Always force of gravity downwards. Then it's not moving up and down, it's being pushed to the right, let's say. So there has to be a force upwards that cancels out the gravity. If not, it would be falling down. So this again, just as in the example of the book lying on a table, is normal force. Always when we have an object on a surface, there is weight and there is normal force, and they are exactly the same. Now let's worry about what it says. It's being pushed through a rough surface. If it's being pushed, we're going to have, let's say, a rightward force that we can call F push, just so that we know what we're talking about. It's to the right. But we also know that it's a rough surface. So what we learned last class is that there's going to be friction. Friction always opposes motion. So if someone is trying to push to the right, friction is going to be to the left. Now, just like in the example of the force of air resistance, friction can't be bigger than the pushing force, because if not, that meant you would push and the box would go the opposite direction, which makes no sense. So friction force, which we call FF, that's why I drew a smaller arrow to show that it's stopping a little, it's making it harder to move, but it's not big enough to push it to the left. And that's it. These are 4 examples that I have for you, and the tips would just be always start with the force of gravity, see if there's a surface in case you need normal force, see if there's something that needs to be canceled out, like here with tension, and then look at what's happening with the object, if it's moving to the right, if there is friction, or something else like that.